Hello, this project is by Eric Northam and Anthony Palladino and is on the I-35 West Highway Bridge Collapse. I-35 West Bridge Collapse occurred in Minneapolis, Minnesota in August of 2007. It is one of the major thoroughfares into and out of Minneapolis. And although there are many documented cases of bridge collapses, two burials brought a great deal of attention to the I-35 collapse. Number one is considered a modern era bridge construction, built in 1967. As such, you'll find many similar constructions throughout the United States using this design. Number two, variable that brought a lot of attention to it was the fact that the failure occurred during evening rush hour and resulted in a high number of fatalities and injuries. Today we'll cover an overview of the bridge design, go into the risk management plan, functional block diagrams, reliability block diagrams, analysis of a beam failure via both a fault tree analysis and an event tree analysis, recommendations for improvement of future bridge designs, and finally a summary of the lessons learned from the catastrophic failure of the bridge collapse. Getting into the design. As previously mentioned, the bridge was constructed in 1967. It was officially known as Bridge 9340. It was an 8-lane steel truss arch bridge that carried Interstate I-35 West across the St. Anthony's Falls of the Mississippi River in Minneapolis, Minnesota. The bridge was Minnesota's third busiest carrying bridge with 140,000 vehicles on average per day. The bridge's span extended a little over 1,900 feet, with the center one a little over 1,000 being supported via deck truss. The three main spans between piers 5 and 8 were of deck truss construction, while all but 2 of the 11 approach spans between piers 2 and 12 were still multi-girdered, and the remaining 2 being of concrete slab construction. The center span was connected to the north and south approaches by shorter spans formed by the same main trusses. The piers were not built in the navigation channel. Instead, the center span of the bridge consisted of a single 458-foot steel arch truss over the 390-foot channel. The 2 support piers for the main trusses, each with 2 load-bearing concrete pylons on either side of the center main span, were located on the opposite banks of the river, not in the water itself. The 2 main trusses, one on either side, ranged in depth from 60 feet above their pier and concrete pylon supports to 36 feet at midspan on the central span and 30 feet deep at the outer ends of the adjoining spans. At the top of the main trusses was the deck truss, 12 feet in depth and integrated with the main trusses. The roadway deck was approximately 115 feet above the water level. The traverse deck beams, part of the deck truss, rested on top of the main trusses. These deck beams supported longitudinal deck stingers 27 inches in depth, as depicted in the picture, and reinforced concrete pavement. The deck was 113 feet 4 inches in width and was split longitudinally. It had transverse expansion joints at the centers and ends of each of the 3 main spans to account for expansion and contraction during temperature changes. Now we're going to go into the proposed risk management plan. There's 5 primary members of the team. It consisted of a bridge chief engineer, risk managers, state bridge engineer, Minnesota Department of Transportation representative, and a lead bridge designer. It involved 4 major phases: a risk identification, risk analysis, risk response planning, and risk monitoring and control. Risk identification: identify the risks and we documented them in a risk register as depicted similar to one on the right there. And it was conducted continuously throughout by all members using systematic top-level and low-level methods. Risk analysis was done. Basically, each risk was scored against the risk scoring matrix for probability of occurrence and the impact if it should occur, using a stoplight chart, red, yellow, and green. Anything that was in the medium or high or yellow and red required a mitigation to reduce the risk to the bridge. The risk response planning develop appropriate options and action plans to reduce the threat of specific risks to project objectives. And then it would update the risk register with a proposed response plan. Risk monitoring was a process of identifying, analyzing, and planning for newly identified risks. monitoring the previously identified ones, reevaluating existing ones, verifying that the response plan strategies were being effective in their use. Basically, two parts there: the monitoring and control. Monitoring is done through periodic reviews, usually on an annual basis. Make sure all the requirements are being implemented during the design phase. Evaluate the effectiveness of the mitigation strategies for any of the risks that have been identified, and then potentially identify new risks as the process goes along, or then in the sustainment phase. Mitigate control was we validate the risk mitigation, take corrective actions if they are warranted, assess the impact on project, identify new risks from risk mitigation actions, and lastly, if there's any new risks as a result of the mitigation, make sure those get implemented and recorded in the risk registrar. Functional block diagram. The basic bridge, we broke it down into, had three primary functions. One, it had to be able to hold loads, to support the structural loads. So this is longitudinal, lateral, shear, vertical, compression, expansion loads. Next, it had to be able to move two-way traffic. So support moving traffic, stagnant traffic, whether it's broken down or just rush hour. And lastly, be able to allow the forwardability or the availability for emergency traffic or emergency vehicles to have access to the bridge, regardless of the status of the traffic. And then the last thing was resist the effects of the environment. So this could be temperature, wind, earthquakes, and with it being over the Mississippi River known to flood, being able to deal with flooding issues. Depicted here is the bridge's hierarchical function breakdown. Configuration flow diagram basically shows all the actual components in the bridge to accomplish the functions previously described in the function block diagram. And here's the hierarchical component breakdown for the bridge. This is the reliability block diagram for the I-35 bridge. The first two parallel systems are the various transverse surface area coatings, as well as their immediate subsurface concrete mixture where cars can drive. If a component were to fail, drivers could simply utilize another portion of the transverse surface area. The support structure below the main trusses are modeled in parallel as well, since the alternative support structures will carry the remaining redistributed load if a component were to fail. The various levels of beams and trusses were modeled in series, since the failure of any of these levels would cause a catastrophic failure of the entire bridge. Actual component reliabilities cannot be found through research, so estimates were given based on importance. A total reliability of 92.65% was calculated given the diagram structure and the reliability estimates. I'll get into the analysis. The group covered two failures that could result in I-35 catastrophic bridge failure. There was the beam failure and then a substructure failure. Due to the time constraints, we're only going to cover the beam failure. Of note that the beam failure is a subset of the actually substructure failure that was analyzed as well. They had very similar events and barriers to mitigate that were played into it. Here's a fault tree analysis for the beam failure. Occurred as a combination of either overloading, vehicle collision. This could either be if the high water ship ran into the concrete piers, or a collision of cars either underneath, because cars were able to drive underneath it, colliding into those piers, or into with a crash on the bridge itself, and leaking all of those corrosive materials, hide fluid, fuel, and everything down into the system. And then lastly was just the overall corrosion of the beam. This came through those cracks, basically through improper sealant, poor concrete overstressed, and then chloride exposure, being able to get in there from the de-icing or a chemical spill, getting into those cracks and reducing the integrity of a beam. Here's a reliability block diagram. Depicts what was shown on the previous slide. Top level event of the beam failure had a probability of 5% based off these numbers. Though in real life, expect this to be significantly less, with the actual numbers being used being significantly different than what was actually used for this. Now we're getting to the event tree analysis for a beam failure. The event tree analysis was created using the probabilities determined from the fault tree analysis that we just looked at. The initiating event was a high traffic load. There were two additional events that were considered. One was the construction equipment being present on the bridge, and the other one was whether or not salt or corrosion took place there. There were 8 barriers were also implemented in order to contain, prevent, or mitigate undesirable exposures to a beam failure. Those barriers consisted of spread loading of construction equipment, incorporating various load monitoring systems, and regulating the throughput of traffic. Now, most of these barriers were not actually implemented on the bridge. These would come into as recommendations down the road that could have helped alleviated the load or the overloading of the bridge that resulted in the collapse of the bridge. Over on the right-hand side, you can see the depicted outcomes. There were 24 possible outcomes in this scenario. 2 resulted in a failure, indicated in red, and there were 2 down there at the bottom resulted in no failure. The remaining 20 result in some sort of degradation of the beam. This is commonly seen if you go to any bridge out there. There's stress fractures or rusting could cause through corrosion that they're not going to be able to hold up the total load that they were initially designed for, which is a lot of times why we see bridges having the construction being done on them. Based off of the analysis, that's some of the recommendations they really need to do if there's construction or reconstruction or maintenance needs to be done on a bridge, and anticipate a heavy volume of equipment or materials, to be very deliberate in the planning of the stages, of understanding what the load is of the bridge, and to plan accordingly, not to have all your everything over one small point and now it's overloading that particular portion of the bridge. Account for resurfacing. So every couple years they go out and resurface the roads, and a lot of times they don't pull it all up, and so end up continue resurfacing, putting new concrete or asphalt down or whatever it may be. And what you'll see is you'll increase the static load that is not initially in the design of the bridge. Incorporate a monitoring system with the electronics we have out there today, where it should be able to monitor, put strain gauges on the critical points, and be able to assess how the loads of the bridge are going. Incorporate that also with an automatic traffic flow control system. So if the bridge is sensing it's getting overloaded, you can use it either through a gate system or a light system, kind of like they do out in I-5 out in California, to relegate the amount of traffic that is flowing over the bridge if it deems it could help reduce the load at a single point in time. And lastly, one of the things, particularly for the I-35, that they realize in a lot of bridges around the world, with the de-icing using chloride that gets into the cracks, and it really attacks the integrity of the steel beams once that corrosion gets put on it. They try to use fresh water, rinse it out, but it doesn't get it, and over time it deteriorates or reduces the integrity of the steel structures on the bridges. So in summary, on August 1st, 2007, a little after 6 o'clock, there was a catastrophic failure of the I-35 bridge, the main span of the deck truss, resulting in over 1,000 feet of it collapsing when the center portion all fallen into the water. 111 vehicles were destroyed, 13 deaths, and over 140 people were injured in the incident. NTSB's investigation realized there was a failure of the gust plate or one of the beams on the bridge, or multiple beams. Basically, they're just undersized and inadequate to support the intended load of the bridge, particularly with the construction equipment on top of there. And then, as I kind of mentioned before, with the resurfacing, realized that the static load on the bridge had increased by upwards of 20% over the years, and it was not accounted for. And the straw that broke the camel's back in this situation was the construction equipment, and the materials were resting above the weakest point at the time of the collapse, and they assessed about 262 tons of sand, vehicle, and water, as depicted in the picture there, resulted in it just the bridge just giving way and not being able to support the loads. That wraps up the I-35 West bridge collapse. For more information, the link down there at the bottom is to the NTSB investigation into the collapse itself, with much more analysis into the disaster.